Hey guys, what do you think of this 3D model of the Washington Monument I've been building for the last month? It's perfect, isn't it? Just look at all these flags I've got fluttering in the wind. Well, maybe you think it's a little bit too perfect. Yeah, I was just messing with you. Um, this is the real Washington Monument, okay? And as you can see, it's about my size.
Your size? No, it's not.
What are you saying? You don't believe me?
No, I don't believe you. No.
Come on, just look at it. It's my size.
No, it's not. It's not your size. No.
Now, you may be used to seeing it bigger, but don't worry about that. It can grow. Watch this. Grow! This is the real Washington Monument. It's about my size. Maybe the way that you think about three-dimensional reality is actually a cosmic illusion. Wow, this thing is humongous. I told you I could make it grow. I just seemed to move my legs and it grew and it grew and it grew this big. Now that's magic, but it's not make-believe. It comes right out of a groundbreaking theory at the edge of modern physics. Two of its continents, quantum mechanics and general relativity, are on a collision course, and something has to give. Welcome to my world. Stick with me, and maybe by the end of this video, you too can understand the magic that is behind space-time. But before we go into all the mysteries of quantum gravity, we're going to have to retrain our brains. We're going to have to drop some of our deep-seated prejudices and assumptions about this universe. And to do that, we need to go into a kind of mental gymnasium. And what better place than my office? Okay? So come on. Well, welcome to the University of Maryland. My name is Raman Sundrum, and I'm a theoretical physicist working here. And I work on all of, look, forget all that. Where were we? Remember at the Washington Monument, we saw how things that were close to us or far from us, like the Washington Monument, looked like they were huge or small? Maybe that apparent illusion is actually closer to the truth. And maybe the way that you think about three-dimensional reality is actually a cosmic illusion. Let's explore that. And to do that, I'd like to go back to pen and paper. So here I have a flat piece of paper. It's conveniently two-dimensional. And we can see why it's two-dimensional. We can count the dimensions. One of the dimensions is the sort of vertical dimension. The other direction we could call the sideways dimension. Those are the two dimensions that we normally think of as a two-dimensional piece of paper. But wait a second. Somebody has gone and put a blotch on my nice new piece of paper. What's going on here? Whoa, 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 whoa! Gosh, that really looked like the train was coming right out at me, right out of the third dimension. But of course, it was kind of a fake third dimension. It was kind of the illusion of depth. It was just really, when you look at it carefully, it's like the train was just getting bigger on the piece of paper. Everything was happening in two dimensions. but it gave the illusion of springing out at me from a third dimension that wasn't actually there. And you can see how it works, that in 2 dimensions, the shape of the train just could be shrunk or magnified. And by doing that, it looks like it's either further away in the depth direction or the third dimension of depth, or closer in that way if it was bigger. You're used to that kind of thing in artwork or in animation. And the way it works is that there are certain shapes, like the shape of a train, that are so distinctive, we associate them with 3-dimensional objects with characteristic sizes. For example, when you see that train, you imagine that that front cabin where the drivers sit is say, the size of this room, right? You know that association. And we could call that association of the characteristic shape with some sort of characteristic size, we could call that a shape-size correlation. We are trained to have these correlations in our head, and we use it to determine whether something is close to us or far from us. So let's have a look at a second example of a kind of shape-size correlation that you're used to. For example, if I were to draw a picture of a little girl, so here is a little girl, and as soon as you see that shape, that's sort of the association you make, that it's a little girl at some distance, right? Because somebody with that shape would typically be about this size, but if they look like that size, then it creates the illusion that they're far away from you. And if I draw the same shape by just magnifying this, say to that size, okay, same shape, just bigger, then it looks like the girl is standing there, but a little bit closer to us, right? So we have the illusion of depth. And you're used to this. You may not think about it a lot, but you're used to this. In fact, if you navigate through your apparently 3-dimensional life, you can see that as you move around and you get closer to the cup, it looks like the cup is bigger. And if you get further away, the cup looks smaller, and you call it getting further away. But what you're experiencing is just big cup, little cup, okay? So that's the shape-size correlation, and you're using it to make sense of your experience here, to tell you about your 3-dimensional experience, or what you think is a 3-dimensional experience. We take the shape-size correlation so much for granted as we navigate around. We don't know that we are doing any interpreting, that a good way to understand it is in cases where the shape-size correlation breaks down. So there's a characteristic shape, absolutely recognizable, but it doesn't have the expected size. And then that throws off your detective work. And you can really see that you're doing a kind of detective work. You can recognize how active your brain is in interpreting reality. So the shape-size correlation can break down. In fact, let me break it and show you. I think for that, I'm going to need my lucky pencil. And I have it here somewhere. I hope I didn't lend it to my student. Let me see. Oh, found it. Okay. Well, there it is. Okay. And you can see it's got a very characteristic shape, the shape of a pencil that you would normally think you'd associate with being that size. But it's this size, and it threw you off in terms of what you thought you were looking at. So that's a way in which the shape-size correlation can break down when I'm really messing with you. But most of the time, the shape-size correlation works the way you expect, and it gives you this very smooth experience of being in 3 dimensions. So could it really be that 3 dimensions is a kind of optical illusion, where we really live fundamentally in a 2-dimensional universe with shapes, distinctive shapes that change their sizes and create the impression of being in 3 dimensions? I know that sounds absolutely crazy, right? But as somebody who works in fundamental physics, I know that the world, the universe, is already completely crazy, completely mind-boggling. But if we're going to accept the idea that three-dimensionality is a cosmic illusion, we'd have to ask a couple of questions before we just accept that preposterous idea. One is, why? Why would you think that that's the case when it doesn't seem on the surface to be the case? What's the detective work, the scientific detective work that leads you to take that idea seriously? The second thing is, if that is what's going on, then what are the mechanics behind it? How is the illusion being created? And it's not being created by somebody to try and trick you. It would have to be some sort of naturally occurring illusion, like the illusion of a mirage in a desert. But in this case, what are the mechanics? Because it's not just that there's an illusion in some particular place, it's the entire universe is a three-dimensional illusion. How does that work? So the reasons go back to attempts to unify general relativity and quantum mechanics within fundamental physics. These are two of the overarching pillars of modern physics and, in some sense, in science. And yet the way in which they fit together is still mysterious. General relativity is Einstein's modern theory of gravity. It's a theory of curved space-time, and it has been fantastically well tested in the over 100 years that it's been around. It is in accord with the detailed movements of planets and satellites. It describes the expansion of the universe as a whole. It describes bending of light by stars and by entire galaxies. It is a theory of gravitational waves, which we can see today, or we can detect today. So, an incredible theory, an incredible success scientifically. Quantum mechanics, it describes a lot of phenomena that we see at microscopic levels. It is the basis for understanding atomic structure and atomic physics, and through that, through all of chemistry and a lot of modern biology. So again, fantastically well tested. Somehow, nature allows these two giants to coexist, but how they do that is very mysterious and, in a sense, paradoxical. A lot of the early detective work and how these two could fit together came from studying black holes. Now, black holes themselves are an amazing prediction of general relativity, a kind of ball of pure gravity, but they remain tremendously mysterious. So in the 1970s, the famous theoretical physicist Stephen Hawking started to study how quantum mechanics would behave in the vicinity of black holes, these very strong gravitational fields. And at that time, people knew what many of us sort of say, that nothing comes out of a black hole. But strictly, that's true at the level of not having quantum mechanics, what's called classical physics. When Hawking studied quantum mechanics around black holes, he found a surprise that something was coming out of black holes, or he predicted that something had to come out of black holes. And that something is what we now call Hawking radiation, after him. So this prediction of Hawking radiation, that it had to be possible, it had to happen, led to a whole series of theoretical deductions, which only made black holes seem even more and more mysterious when you try to confront quantum mechanics and gravity in the same regime. It ultimately led to a paradox, which is called the black hole information paradox. It has a number of aspects, but let's talk about the parts that are related to our driving question about dimensionality. So before we talk about what physicists mean when they say information in that way, let's ask what regular people mean by information. When I think of that, I think of like books in a library, and each of the books has lots of words and letters inside them. So let's take that picture of information. and compare 2 and 3 dimensions. Okay, so here is a 2-dimensional space. It's a square. It's a square with sides L and L, and I've drawn the case L equals 4, where in each of the little cubes that you get, I'm going to put one letter of information. And using that, I can write some sort of a message. And you can ask, how much information can I get in there? And if each side is L, then I can get L times L, or L squared, letters of information. Okay, so that's a measure of how much information I can get in there. Now, the only difference for a physicist is they're not looking at letters of the English alphabet for information. They're trying to gauge how many quantum states they can have in that region. And the one important distinction for us with quantum states is, especially in a theory in which gravity is there, quantum gravity, there is a minimum size to this unit cell in which you're dropping each letter. Okay, the minimum size is what's called the Planck length. Okay, so L Planck is the way it's usually written, and it's a distance of which is really tiny, 10 to the minus 33 centimeters. Okay, so that is way, 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 way smaller than an atom. Okay, which is already small. But other than that, telling you that there's a smallest distance that you can write on, information is a bit like the letters on this board here. Okay, now the comparison I want to make is with 3 dimensions, where again I can take a finite region of space, which in this case I've drawn as an L by L by L cube. And again, in each of the little subcells or the little subcubes that you're seeing here, I can drop a letter of the alphabet. And in doing so, I can write some message or code of information. And you can ask again, how long is that? How big is that information content? And clearly, it's the number of these individual cells, L times L times L, or L cubed, letters of information. So you can see that this 3 here is the 3 of 3 dimensions. This 2 here is the 2 of 2 dimensions. And what you can see is that for large L, there's just lots more information that you can pack into this 3-dimensional L-sized volume compared to the analogous 2-dimensional space. It's just matching our intuition. 3 dimensions is more spacious, it's richer in possibility compared to 2 dimensions. Okay, so there's a vast difference. Now, after Hawking predicted Hawking radiation and that there was a temperature, Hawking temperature, associated with that radiation that was necessary in black holes, it led to the subject of trying to figure out how much information could be packed into the black hole. Okay, and there was a surprising result. Okay, and it was put in its more succinct form by Jacob Bekenstein in what's called the Bekenstein bound now, but basically studying 3-dimensional black holes and asking how much information can be packed in there. And the remarkable result, drum roll, was it wasn't L cubed. It wasn't this. Okay, even though they're 3-dimensional black holes, it was L squared. So something bizarre was going on. So what's going on with the L squared? Well, it's really the area around the black hole. The black hole information is secretly encoded in the area around the black hole, or the so-called black hole horizon. Now, you have to remember that black holes are already the densest objects possible in a world which has gravity in it. After all, black holes naturally form when stars collapse, getting ever denser, and when they're dense enough, they turn into black holes, the densest things possible. And if even the most densely packed regions of space have information content that goes like L squared, the area around them, then that must be true of any volume of space, even if it doesn't have black holes in it. Any volume of space, any region of space can only have information that that's encoded in the surface that surrounds that region of space. This was put into the most succinct form by the Nobel Prize winner Gerard Tufte, who got his Nobel Prize for something completely different. He basically gave rise to what we call the holographic principle of quantum gravity. And that is that secretly there is a two-dimensional theory which has all the information in it that creates the illusion of a three-dimensional reality that we apparently walk around in. So the world or the universe is fundamentally two-dimensional, very much like holograms or holographic animation. The question is, how exactly could that work? How could a two-dimensional theory or two-dimensional mechanism give rise to a three-dimensional apparent reality? The gods of quantum gravity have spoken, and they say, make thy 3D house from 2D bricks. And at the level of the entire universe, that means that our apparently three-dimensional universe, with people and stars and atoms, all of that is an illusion. But that illusion is being projected by some kind of two-dimensional reality surrounding it. But to understand how that's even possible, we're going to have to take a few steps back. We can't keep talking at the level of pencils and trains. We have to ask, what are they fundamentally made out of? And of course, fundamentally, they're made out of atoms moving around in a supposedly three-dimensional universe. Atoms, or atomic physics, are described by the strange laws of quantum mechanics. Quantum mechanics predicts that atoms or atomic orbitals have these very beautiful and discrete shapes. And each of these discrete shapes comes in some very distinctive microscopic size. So there's a tight shape-size correlation at the level of atomic physics. And we can try to picture that because I've been playing with my blocks here, where you can see they also come in very different shapes, but discrete ones out of the pack. And the same shapes come in exactly the same sizes. Okay? So if one of these identical shapes is bigger than the other, then you can safely assume that that's because the bigger one is closer and the smaller one further in this third dimension of depth. Now, these distinctive atomic shapes can be glued together. They can be attached in various interesting ways in order to make more complex structures, such as molecules. And putting those together, you can get things like tables and chairs and trains and pencils. So these macroscopic objects built out of atoms inherit the shape-size correlation that's fundamentally there at atomic level. And in that way, our three-dimensional macroscopic experience with known shape-size correlations backs into atomic physics, and there's a beautiful self-consistent picture or theory of a solidly three-dimensional world with a tight shape-size correlation. Okay? So much so, it works so well that you'd wonder, why to question it at all. Okay. Now, quantum mechanics is a subject that's now about a century old, and it has been fantastically well tested. And you could really say, well, what has sort of been the peak of the developments in the last century? And that really is its unification with the other pillar of modern physics, which is relativity, and in particular, Einstein's theory of special relativity. Okay, so 3D quantum mechanics. So 3D quantum mechanics and special relativity. Special relativity is the strange and bizarre way that objects and clocks behave when traveling close to the speed of light. Okay, very unintuitive things happen in that regime. Just like very unintuitive things happen when you go to very microscopic scales at the level of atoms. So these two revolutionary breaks with our ordinary intuition, when unified, give rise to an even more amazing structure, which is called quantum field theory. Okay, so quantum mechanics merged, fused, unified in a very non-trivial way with special relativity gives rise to quantum field theory, the ultimate grammar that we have tested. And it is the basis for modern physics, which is in turn the basis for modern chemistry, which is in turn the basis for modern biology, engineering, you name it, okay, our understanding of the physical universe. All of this so well tested, and yet, because it is based on three-dimensional bricks, it's based on three-dimensional atoms, the entire thing violates what our insights from quantum gravity would suggest. And that means that however fantastic this is, it must ultimately be wrong. So it's got to go. At best, it can come back as a kind of approximation to the truth or a description of the illusion, but not the fundamental truth. For that, we're going to have to start the whole game again. We're going to have to again go back to quantum mechanics and special relativity, but in a two-dimensional universe, okay? So when you put quantum mechanics and special relativity together, but now in two dimensions, you get a two-dimensional quantum field theory, and it has some sort of two-dimensional atomic shapes, some sort of discrete shapes. But remember, that's not the point to have a two-dimensional world. You want the illusion of a three-dimensional world. So if we want to create that illusion, right, we can see, let me just draw these over here, right, like that. It's crucial that these two-dimensional atoms should not have a fixed size. They should have a variable size like this so that they can look closer or further in an illusionary third dimension. Okay, so we have to add one more principle, which is variable size. Okay, so when you put these three axioms or principles together, you don't just get a typical quantum field theory. You get in two dimensions, you get what is called a conformal field theory. Conformal field theory has been studied because it describes a body of experiments completely different from quantum gravity or anything that we've been talking about. And it's been studied for decades, and also studied because of its beautiful mathematical properties. But I want to focus on just sort of three of its magical properties that are key to this sort of holographic illusion, okay? So the first property I want to talk about is something we could call, in the language of conformal field theory, scaling behavior, okay? And it describes how objects with different amounts of rescaling of their size interact with each other. You see, because we're facing a funny problem here. If this is an illusion of two objects in a third dimension, then one of the things you're used to is that in real three dimensions, they can pass by each other. It looks like they're going to collide if you're just looking from your angle, but actually they don't collide, they pass by each other. Now, if the fundamental truth is these are shapes in two dimensions. So if this guy is moving in this direction, it's crucial that it should seemingly pass by, that the two shapes should not interact. And that is a beautiful consequence of this scaling behavior that is possible in conformal field theory. So that's magic step number one. Now, the second property is what's called conformal symmetry. And conformal symmetry is the thing that puts the word conformal in conformal field theory or conformal quantum field theories. Okay, that's the word conformal. And it relates to the following thing, that you'll see that all of my pictures in 2 dimensions are a little bit like those ancient Egyptian paintings where everybody is always in profile, but you never see interesting angles like that. So here too, you might say, look, it's not good enough to just be able to capture this aspect of this 3-dimensional block. I want the illusion of 3-dimensionality. I need to be able to see it at other angles. Okay? So it's crucial that there should be these shapes, atomic shapes in 2 dimensions, which are matches for these other views where you've rotated 2 dimensions into the fake 3rd dimension. Okay, so let's capture that. Okay, so we would need this kind of shape to be one of the atomic shapes that this 2-dimensional theory would have automatically. The amazing thing is that a consequence of having variable size in quantum field theory is it gives rise to conformal symmetry, and conformal symmetry is the statement that there are all these related shapes. So there's still one thing missing in our story, and that's gravity. Gravity, the reason why we're doing all of this, okay? And in fact, in this fusion of quantum mechanics and relativity, the word special is referring to the absence of gravity. Gravity is the theory of general relativity. So at the moment, it doesn't seem to be there. But there is a third property of conformal field theories, okay? And in fact, of quantum field theories more generally. And that is the principle of locality. Now, locality is the principle that two objects can only ever interact if they're at the same place at the same time. There's no such thing in a relativistic theory as action at a distance. That's the principle of locality. And in the illusion that conformal field theories give rise to, this principle of locality gives rise to, wait for it, gravity, okay? So there's an illusion of 3D gravity. The gravity isn't there in reality in the 2-dimensional formulation of the theory, but just as an extra dimension emerges as an illusion, so does 3-dimensional gravity. This formulation of a holographic theory in which a 2-dimensional theory gives rise to the illusion of a 3-dimensional universe with gravity is now one of our best developed theories of the quantum gravity holographic principle. It's primarily due to the insights of the theoretical physicist Juan Maldacena, who is currently working at the Institute of Advanced Studies in Princeton, the same institution which hosted Einstein in his later years. And it is one of our best laboratories, if you want, for understanding the information paradox and how it gets resolved. The key to how the information paradox is resolved can be thought of in analogy with another kind of paradox I could phrase. Imagine you're walking in the desert, you see a pool of water, and the paradox is, how can I walk through the pool of water and come out with my feet dry? So at first, again, taken on its own terms, it seems like you can't solve that paradox. But once you realize that that pool of water is a mirage, then of course you can walk right into it, walk right out, and your feet are dry. There's the same taste of that paradox and the information paradox in how it is resolved, in this case, by gravity being part of the mirage. So in the same way, the seemingly irreconcilable confrontation of quantum mechanics and gravity ends up being reconciled by the fact that gravity is itself a mirage.
So I've mostly been explaining the holographic principle of quantum gravity in terms of our visual experience. But we do have other senses, like we can hear, or touch, or smell, or taste. And we only smell things or touch them when they're close by, but not when they're far away. And in that way, and many other ways, our senses seem to back up a rich and in-depth 3D experience. How do you fake all of that? So the key thing to remember is that you're not just sitting in a chair watching a two-dimensional movie screen portraying a three-dimensional world. You're part of the movie. Your body and your brain and all your sense organs are complex two-dimensional shapes on the cosmic screen itself. And our sense organs function according to their chemistry. And that chemistry is derived ultimately from the workings of atoms. So once the illusion of three-dimensionality is set up at the level of the fundamental building blocks, as we've discussed, that extends to all our senses.
So this holographic projection of a gravitating spacetime by conformal field theory is one of the biggest discoveries in theoretical physics in the last few decades. And I've been calling it a kind of illusion, a cosmic illusion. And that word illusion is a little bit wrong. Because when you say the word illusion, you really mean that there is a possibility of discovering the error that it is an illusion. So, for example, if you have an illusion like a mirage in the desert, then it looks like you can see a puddle of water, but when you get close to it, you discover it's not a puddle of water, it's just some hot air. And so that's the sense of the word illusion, that it can be discovered to be an illusion. But the holographic projection mechanism is so perfect that you can't catch it out. You can't discover it's only an illusion. It really deserves a different word than that. And the word physicists have for that situation is duality. So in a duality, you have two descriptions of the same reality, which are equally valid. It's not like one is the fake and the other is the real thing. They're equally valid, and yet they seem to contradict each other. In this case, it's saying that the world is three-dimensional. Oh, no, the world is two-dimensional. They seem to be opposed to each other, but secretly they're not. The classic and more familiar case of duality in everyday life is the proverbial glass half full or the glass half empty. Full and empty seem to be somehow opposed to each other, but the glass half full and the glass half empty is pointing to precisely this reality that you see here. There's another confession I have to make. So our universe is famously expanding, and the galaxy clusters are getting further and further away from each other as the fabric of space expands. And that expanding space-time is approximately described by one of the very early solutions to Einstein's equations called de Sitter spacetime, after its discoverer. Now, it turns out that the space-time that's projected by conformal field theory is not an expanding space-time. Instead, it has the opposite kind of curvature of space-time than de Sitter space, and therefore it's called anti-de Sitter space-time. And so the duality that we've been discussing for the entire video has a name, technically, which you can now understand. It's called anti-de Sitter, or ADS for short, slash CFT, or conformal field theory, duality. Okay? So these are the two sides of how you're viewing the glass half full, glass half empty aspect that we call a duality. Now, at the level of the scale of this room or even the solar system, the distinction between de Sitter spacetime and anti-de Sitter spacetime is really not that important. So there's a lot of, if you like, truth that we can take from the ADS-CFT duality, even with respect to our universe. But in detail, it's not the real thing. ADS-CFT in detail does not apply to our universe. Now, the discovery of ADS-CFT duality theoretically has led to a host of different explorations that are still ongoing. It's still being mined for insights and hoping to get ever closer to the real universe that we live in. So obviously, one of the big questions is, how would holography work in expanding universes like the one that we actually live in? That's a hot question, and we still are looking for the answers to that. Another question would be, if something like holography is taking place in our universe, are there aspects of it that can be tested experimentally? It relates to my own work, but it also involves even more exotic ingredients like higher dimensional space-time. And I'm hoping that some of these topics that I can get to in further videos. For the moment, maybe this is a good place to stop. What do you think? You think this is a good place to stop?
Yeah, I think my brain is exploding now.
Well, okay then. So, thanks for watching, guys. I've linked below some extra resources for you in case you're interested. And until next time. Where was I?